So I do sections 10.4 and 10.5. I call it radius of convergence. So first we figure out, I'm going to be giving you a bunch of different tests to figure out if a series converges to a sum. So if we can find that sum. And then I'm going to be giving you what the radius of convergence is and the interval of convergence. So our book kind of does these almost interchangeably. So I've kind of broken the videos up into a few days. So our first test is the nth term for divergence. Now the key word there is divergence. And I want to call this the weakest of all the tests. So this is the nth term for divergence. So really all we can do is with this test is prove that a series diverges. We don't know if it can converge. So our nth term for divergence says that if we have the limit and it doesn't equal 0 or fails to exist, that it diverges. So basically said another way is if the limit equals 0, we could converge. We don't have to, and that's why I'm going to be giving us a whole bunch more tests. So our first example here, let's look at the limit as n goes to infinity of this n minus 1 over n plus 1. Now what is that limit? That limit equals 1. So since the limit doesn't equal 0, or it fails to exist, it technically equals a number. That means that this series diverges. Okay, our limit has to equal 0 for it to potentially converge. Okay, geometric series. We've kind of talked about these already, and we actually did some problems earlier with this in the chapter. So we're given a series either where we're given some coefficient times x minus a to some exponent. So the only time that we see n is when it's in an exponent. Series converges only when this, which is your ratio, this is your ratio, is between -1 and 1. Then remember the sum of the convergent series is, I like to call that the first term. I don't know why a sub k is in there. Our first term over 1 minus the ratio. We've been doing a few examples like this already. So just as a reminder, finding the interval of convergence for this. Recognize right away it is geometric. That's what you need to recognize. I recognize that because I have something to the n power, and that's the only place that I see the n. And now finding the interval of convergence for this. Your 2x minus 1 over 3 is going to be between -1 and 1. Now our book talks about the radius of convergence. And what that is if you get your ratio, into the form of x minus some a, the absolute value of that, less than whatever r is. That's your radius of convergence, and this is the center of our interval of convergence, where our series is centered around. So I kind of want to show you guys how to get the radius of convergence for this. Remember that this thing is the same thing that I have here. I'm going to multiply both sides by 3. Now I need to get this into x minus a, so the coefficient on x has to be 1. So if I divide by 2, we now have that in this form, where it's x minus a. I didn't divide everything by 2. I need to have this divided by 2 also. So in this case, our radius is going to be 3/2, where our center is 1/2. Now, if I add 1/2 to both sides, I am going to get -1 less than x less than 2. So this is our interval of convergence. Now remember, our center was halfway in between -1 and 2. What's halfway in between -1 and 2? 1/2. Okay, what's the distance from 1/2 to either one of my endpoints? Well, my radius is. All right, pSeries test. This chapter, this section, is why we did the pSeries test for our improper integrals that we covered in chapter 9. So remember that if we have a polynomial where we have 1 over n to some value, 1 over n to some value, this series is going to diverge if p is less than or equal to 1. The only way we're going to converge is if this exponent is greater than 1. So looking at this example. What's the exponent there? The exponent in this case is n to the 3/2. Technically, using some rules of summation, we can make it like that so that we can show that it's 1 over. Now, 3/2 is greater than 1, so therefore our series converges by the pSeries test. And I want you guys to kind of write that. And we're going to be doing so many more examples of this, but please tell me the test that you're using. Okay, another test that we talked about was direct comparison test. The test is used when a known series is bigger than a given series. Okay, so keep this in mind. This is our known series, and this is the one that was given to us in the problem. Okay, and what we're going to be doing is we're going to be comparing the bigger function to the smaller function. Now, if the bigger function, remember that means that that is a ceiling function. The ceiling function converges, goes to a sum, then the one that's below it, the one that's a little less than it, is going to also converge. Now remember, so I'm going to write ceiling on there. Let's see if I can spell ceiling right. Oh, good. It was in my notes, so I was able to spell it right. Okay. Now here, again, b of n is our known function. So we're comparing some known function to the function that we were given. And this is considered a floor function. So if the bigger of the function diverges, then the smaller of the functions must also diverge because it's on the floor, but it's going up to some value. Okay, let's do an example of this. And I think, if I remember correctly, we did this in that improper integrals also. Okay, show that that series converges. So in this example, I remember you guys, some people were having trouble picking a known series, picking something that converged. So first, pick a convenient function. Okay, pick something. Basically, what you want to do is you want to take away anything that's being added or subtracted. So for this function, I am going to pick the sum of 1 over n squared. Okay, now you need to show the greater than or less than. Okay, since I have a fraction and I'm adding something to this, that's making this fraction, this number bigger on the bottom, which is an overall smaller fraction. Okay, then we need to state in words. And then 3, state in words. Okay, so this is where this gets a lot of fun. Since this function now why does that converge? This converges by the test we just did, our pSeries test. Okay, because our exponent's greater than 1. And since this function is bigger than that function, this is going to some value, so it's forcing this one to go to that value also. So this must also converge by the direct comparison, oh, I spelled it right, good, test. Okay, so all of that should hopefully look familiar. So make this video not too long, I'm going to stop it there, and I'm just going to kind of be building these videos into different links into a page on Schoology.